You are coding a model on your M series Mac, but popular frameworks just aren't cutting it. Slow training, hard to optimize. If that sounds familiar, or you just want to explore better ML tools, you're in the right place of YouTube. Today, we are taking a dive into the basics of mlx, an in-house arrays framework optimized for M series chips. mlx is outperforming competitors in some benchmarks. This is some data I have found online related to this topic. I built this map to showcase all of the sections I will go over in this series. This video will consist of the basics. These are fundamental building blocks which will allow you to maneuver this framework with ease, even if this is your first arrays/machine learning framework you are learning. I'll go over each subsection in order. If you're new to this framework, I suggest sticking around for each subject, since you will make use of all of them later. So this is the notebook I'll be working with today. I'll leave it down in the description if you want to exercise in parallel or take a look after. Over here I imported the required libraries. mlx.core, as I said, will be the main subject of today. I'll use it as mx and also numpy and torch for possible comparisons. Over here we have a simple array initializer. Let me print it. Yep. As we see, this prints out the array 1, 2, 3, 4, 5, 6. This is of data type float 16. I'll just do it again so it sits right with you. Let's say 1. And over here I can add the data type of the array. Let's just say mx.int16. I think this is the default of all arrays. This will be automatically streamed on the GPU, so the GPU will perform all operations. Now I'll go into some simple array operations such as adding and multiplying and also broadcasting really quick, so you get a sense of what will come after. Let's just initialize another array. This is very similar to numpy. You can also change between the two libraries very easily. So let's say we would do something like this. We would have the array as a numpy array, an ND array, how you want to call it. Yeah, let's get back to the operations. So let's say 5, 6, 7, 8. We can add them as you would in numpy by doing something like this: 6, 8, 10, 12, 6, 8, 10, 12. This is the addition between these two arrays. You can also use mx.add. That would take in two arguments and it would do the same thing. The advantage of doing this, although sometimes you wouldn't use it, but it's useful, is that you can stream it to the GPU, for example, directly, or CPU. This is a big advantage if you want to use both CPU and GPU for different operations in your program or when you're developing an ML model. As I said, this would go over here. Something like these are also, you can use subtract actually. I don't know why I don't have the shortcuts. So yeah, this is -4 because the difference between each element at each index is 4. So now moving on to broadcasting, I have over here an n-dimensional array. I'm using numpy. So this is a one-dimensional array. Let's say I want to multiply this by 2. That would yield 2, 4, 6. What numpy does, you can just multiply it by 2 directly. It broadcasts the 0-dimensional array technically to 1 dimension. This can be done from 1 dimension to 3 dimensions, from 2 dimensions to 3 dimensions. This is just a simple example. And this would print 2, 4, 6. So if I just do mx array, it will print the exact same thing. So this is very intuitive and it's also very useful. Next is indexing and slicing. So over here I have a two-dimensional array. Each one-dimensional array is composed of 3 elements from 10 to 90 in total. This first command, so just right off the bat, this is exactly like NumPy, so no new elements. The first line over here, the first print statement, prints all the rows in column 1, meaning the second column in computer science terms. So 20, 50, 80. 0 index, first index. The second prints rows 1 and 2, meaning the second and the third row. This is inclusive, meaning the first element starts on index 1 up until the end. This is exclusive, meaning the third column, index 2, doesn't get printed. If we print over here, we get 20, 50, 80 in the first line, and 40, 50 in a 2D array, and 70, 80 to 1D arrays. Moving on to saving and loading arrays. So if I want to save this array, I'll just use mlx.core.saves. Let's say the file name is this will get saved in the same folder as your notebook in this case. And the next parameter is x. You'll just do x equals your array name. If I do x1 over here, just to be clear. So now the array is saved. If I want now to load the saved array, I'll just do x1 equals dot load and the file name. Path in the case you have a separate folder with your arrays. I'll just print the result. Yep, so this is the same array as the one that we have saved. Now we are on more operations and function transforms. I'll just list a couple, I noted them here. The exponential, logarithm, square root, sine, and absolute. Just to note, the logarithm is in base e, the natural logarithm, so ln. Maybe you know it as that. Then we also have reductions, such as sum. We'll sum the elements of a tensor. Mean, standard deviation, very useful. Then functional transforms, such as the gradient of a certain function, and value and grad is also useful in the case of machine learning. We also have a vectorization method. This is useful when you want to apply a certain function that you have defined over the whole array. I have an example down here. And also I'm using type conversion. I'll start first with the reductions because it's easier to get through with. This line over here initializes a one-dimensional array with elements ranging from 0 to 11, 11 being exclusive, so the last element will be 10. I think it's pretty straightforward. Now, if we print the mean, standard deviation, and some of these elements, for the mean you expect 5. For the standard deviation, that's a more complicated calculation, but for the sum, pretty straightforward. 11 times 10 over 2, so it's 5 times 11, that will be 55. 55. So 5 for the mean, the standard deviation 3.16, and as I said, sum 55. I'll just delete this so we can move on to operations. So over here, I'll again use arange to initialize an array, but I add 1, so we will have elements 1 through 7 inclusive now because we added the 1 by broadcasting. Another reduction useful, cumulative product. This would print the factorials. So 1, 2, 6, 127, 20, 5040. Very straightforward. Cumulative product, you might use it in some machine learning algorithms. Useful to know. You can also use mlx.core prod of the array you want to print. So same result. A lot of functions could be called in both ways. Depends more on your coding style and application. So moving on, over here I have a function transform example. So again, over here I use arange. So we have elements from 0 to 8. We multiply that by the constant pi. So this is the constant pi. This would yield a one-dimensional array containing elements 0, pi, 2 pi, so on until 7 times pi. If we print the cosine of this array, we would get 1, minus 1, 1. So this is expected. If you're familiar with cosine and operations like this, I expect it to be that way. I'll also delete this. So moving on, here I have the inverse. I called it inverse because it's 1 over x. So if we use the mx.log function and we grad that, we differentiate it to be more specific in this case, we would get 1 over x because that's the derivative of the natural logarithm. We want to apply our inverse function over a whole vector. For that, we use this method mlx.core, in my case mx, dot vector map vmap our inverse function. Over here I have the new function v underscore inv. Second line, so our x contained the element 0. That meant that if I would have applied our function over the vector x, we would have an infinity value. I'll just do that. So if we run the cell over here, I do not have 0 in the array. However, our elements are printed correctly. So 1 over 1 is 1, 1 over 2 is 2, 1 over 3 is 0.3. This is a floating point number, so it's not exact. If I just put x in here, so this is the biggest number that could be allocated to our reserved space for the variable. My third snippet over here, I have the second derivative of the natural logarithm, which would be minus 1 over x to the second power. You can do it on paper, that's the result. So I have applied inverse prime over here. This just means the derivative of the inverse, which is the second derivative of the logarithm. A new array is initialized. X10, this just contains the element 10. I'll also apply the vector map to this function and put it on x to show it to you. So we expect minus 1 over 10 to the second power. That would mean minus 0.01. It's already printed. If I go over here and apply it to x with non-zeros, I'll just apply the vmap to this function. So yeah, 1 over minus 1 over 1 is minus 1, minus the second element would be minus 1 over 2 to the second power, and that would yield minus 1 over 4, which is 0.25. If you want to define your loss functions or initializers, you would use these functions a lot. The most useful ones I would say are the sum, mean, and standard deviation, since those are widely used in probability and statistics, which is, in my opinion, the most important sector of mathematics that's applied in machine learning. Moving on, shape transformations. You would use all of these functions to reshape, transpose your tensors. Widely used in deep learning especially. A lot of algorithms require you to reshape or transpose your tensors, and also in order to match your dimensions when you do these operations, sometimes you have to expand your dimensions or squeeze them. Also, concatenation is widely used in deep learning because you want to make concatenate two different outputs of separate convolutions. We'll get into that later. However, I just wanted to maybe familiarize you with later subjects. Now let's get into it. So over here on the first line I have a one-dimensional array initializer, and over here on the second line I use the reshape function on this array. So the first parameter is the array. You can also use x.reshape. It's essentially the same thing. mlx usually has both definitions, as I earlier said. And the second parameter is a tuple of n, meaning the n dimensions of your array. So over here you can have how many elements you want. The first element of the tuple tells mlx pretty much split this 1D array into 3 parts and figure out the amount of elements of the second dimension. You can only use -1 as a fixed element of the tuple, so you cannot have -1 more than once. This just tells it put the remaining elements such that. So this would yield a 2-dimensional array with 3 rows and 3 columns. This print over here. I'll just show you an example of a 3-dimensional array. So I'll use 2, 2, and -1. Instead of -1, this would be 2 if you would know the exact number of elements you would have in that array. Let's just delete this line because now the array has a different dimension. This line too. So over here, as you can see, this is a 2-dimensional array. This is another 2-dimensional array. So in total, 3 dimensions. You can imagine it, this exact example, as a cube because each dimension has the same amount of elements. Now let's rewind. The second snippet contains the first line, a initializer. This initializes a array full of 1s that has the same shape as x. So x now has the shape of 3 rows, 3 columns, a 2D matrix, because I rewinded from the example I showed you. Now I'm telling mlx I want to concatenate x and x_1 on the second axis. That means the first index. For this method to work properly and not throw an error, you would need to have all the other dimensions of both arrays matching. So in this case, they all match. I'll just print first. So this is x, and this is x concatenated with the array of ones. So another square matrix of 9 elements full of ones were printed. I also missed this. This is a transpose operation. What this does, it switches the order of the dimensions. In this case, if you switch the first and second dimension, index 0 and 1 respectively, you would get an array that is the exact transpose in mathematical terms of x. So if you look, the columns have now become rows. So the first column is the first row, and the first row is the first column in the second one. So if you read it row wise, you would get 1, 2, 3, 4, 5, 6, 7, 8, 9, and on this one, column wise, you would get 1, 2, 3, 4, 5, 6, so on. Now moving on, I'll just give another quick example for the concatenate operation so it cements correctly. For example, if I would have an array such as x2, I'll just define it as that. It does not contain only 2's, but I can do that also. Let's just say I'll get this array, remove the last 3 elements, and reshape it to, I'll use the other way of reshaping, x3 and -1. In this case, -1 would be 2 because I have only 6 elements. I'll just do this so it's not that confusing. So over here I have 1, 2, 3, 4, 5, 6, 7, 8, 9. And over here I have the new array 1, 2, 3, 4, 5, 6 that I concatenated on the second axis. That means that I concatenated the columns because I had matching rows. Now we're on expand dimension function. So this function adds a new dimension to the array. In this case, if we have a 2-dimensional array, a matrix, the basic one we initialized earlier, we can use expand dimension to turn it into a 3-dimensional array, an array with 3 dimensions that would look something like this. So each element is in a 1D array. In mathematical terms, each 1D array with one element is a 0-dimensional array. The squeeze function, if we try to squeeze the third axis at index 2, we will see we get the original array that we earlier initialized. Something to be careful with when working with squeeze is that you cannot squeeze a dimension that has more than one element as the size of that dimension. So in this case, the second dimension, axis 1, has size 3. This means it cannot be squeezed, so just something to pay attention to. Moving on to the stack operation, this is pretty straightforward. I have initialized over here 3 1D arrays. And if we use mlx.stack on these 3 arrays, the parameter works with a list. I think you can also format it in a different way. What it does, you'll get a 2D array that looks exactly like x, and it's the stack of these 3 arrays. So they're stacked upon each other if you want to think about it like that. It's similar to expand dimensions in the sense that it adds a new dimension, but it behaves a little bit more like concatenate, because you concatenate on a new dimension that you do not have. But you cannot get this behavior usually with the concatenate operation. So the stack function is something in of it by itself, just to note that. So this is pretty much how the reshaping operations work. They're pretty straightforward, similar to NumPy and Torch. Very easy to work with. Yeah, you're going to use these a lot in deep learning and a lot of sectors of machine learning. Yeah, so moving on. Now we have reached the linear algebra module. Personally, I haven't used this while I was developing models. However, it's a nice thing to know. Something to note is that most of these operations are, at the moment I'm recording this video, are only supported on the CPU. Excluding matrix multiplication, this is widely used in any machine learning model. Now let's start. So first over here I defined the matrix A 4726 2D square, 2 columns, 2 rows. Over here I have defined the identity matrix. If you're familiar with linear algebra, there are some nice properties to this matrix. So the diagonal is composed of ones. This print statement prints the multiplication of A and the identity matrix. So if I run this cell, so A times the identity matrix equals A. This is as expected. What mlx.all does, it just applies the condition on all the elements. So if I do not use mlx.all, over here I get a 2D matrix where everything is true because the matrices are equal. A times the identity matrix and A. So you can also use the binary operator for matrix multiplication, which is this. The result is the same. This is more convenient when you're writing code, but as I said earlier, this is really dependent on your coding style. Here I have the inverse operation, linear algebra.inv. As I said earlier, this needs to be streamed on the CPU. If you try to stream it on the GPU, you will get a notification error actually, but it says that this operation is not yet supported on the GPU. So I'm going to leave it like that. So if we run this cell, we will get the inverse of A over here. I'll just remove this so it's a little bit more clean. You can throw it into a online algorithm for the inverse, or you can calculate it yourself. Since this is a 2x2 matrix, it should be pretty fast on paper, but you can take my word for it. Over here we have the eigenvalues and eigenvectors of this matrix A. Eigenvalues is the function for eigenvalues and eig is for eigenvectors. So if we run this, we can see that the eigenvalues are complex. We do not really care since this is not a linear algebra tutorial. However, the eigenvalues are used in some data science algorithms. If we scroll down a little bit, over here I have a solution algorithm to a system. So if you are not familiar with linear algebra, over here I have defined a input 11 and 8. It's convenient and easy to calculate and demonstrate, so that's why I chose it. And over here I have the solution. So what this snippet is doing, we need to find a vector, the matrix multiplied by that vector equals the input vector. So this should print 1 1, yes, because 4 times 1 plus 7 times 1, so first row elements multiplied by 1 and 1 as the coefficients equal 11, and same for the second row. So this is pretty straightforward in my opinion. If you're not familiar with linear algebra, I recommend you to take a look at some of these concepts. However, I just threw them in because it is nice to know. You can also read the documentation. You can find some interesting things that maybe I have not covered. Moving on to random, this module, really useful. You're going to use it a lot, especially when sampling. Maybe image generation uses a lot of probabilistic elements, and also batching, cross-validation. All of these will make use of modules like random. So mx.random has a lot of functions. You have a Bernoulli distribution. This is a discrete distribution. You have Laplace, multivariate normal, and so on. The first example here uses a normal distribution or Gaussian distribution, and we sample a shape of 3 by 3. This means a two-dimensional matrix with 3 columns and 3 rows. By default, the normal distribution, the same as in NumPy, the mean is 0, so it's centered at 0, and the standard deviation is 1. So if we sample, we get these values. An interesting example, let's say we have a 20 by 20 square matrix. I'm not going to print that because most of the values are not going to be shown. However, if I print the mean of this, it should be roughly 0. So it tends to 0. If I run it again, so let's say 200 by 200. Yeah, so this is very close to 0. The next example is a uniform distribution, a continuous distribution, same as the Gaussian. Let me just delete this cell. So if we take a look over here, all the values are between 0 and 1. The interesting property of the uniform distribution is that any value between 0 and 1 has the same probability of being sampled. If we do something like 10 by 10 over here and print the mean of our sample, this should be roughly 0.5. Yes, so this is a little bit closer because of the lower standard deviation of the function. You can play around with, let's say, low equals 0, so 1, I'll just use 1, and high equals 10. If we do the same thing and print the mean, this should be 5.5, I think. Yeah, so 5.73. This gets really close while you make the sample larger. So yeah, so this means that the low from 0 gets changed to 1 and the high gets changed from 1 to 10. These are the default params of the function. Now moving on, the random seed is a seed for the randomness in a certain operation. So if two people have the same seed, the reproducibility of the same numbers is possible. However, it is very rare. If you want to really have randomness, you might use something else. This is not a cybersecurity problem, so we do not really care about this in the scope of this tutorial, but maybe if you want to have true randomness, you'll use something like radiation waves from the sun or outside our solar system and use those. Just a quick fact. The next snippet uses the random int function. So this is similar to the uniform, however this is discrete. That means that only integers from 0 to 10 can be sampled. So this would have elements such as this. If we sample something larger and print the mean for this also, 3.97. This is a little bit harder to achieve the true mean on, but if we do 100, we're going to get closer to 5. 100, 1000. This is because it's discrete. There are some interesting properties to all these functions I have listed over here. The Gaussian, however, is the most widely used. It has very interesting properties. It's used in a lot of new algorithms such as diffusion and also VAEs. They're in the same ballpark. And also the uniform distribution. If you want to have, let's say, a good sampling for labels, you might use random integer. This is because your labels are discrete in classification tasks. So you might also use random choice from NumPy. So this is the NumPy function, random choice. It behaves very similarly. What you really want to take into consideration is that you might want to use mlx exclusively while you are coding a model, especially in your training loop. Although mlx is very compatible with NumPy, I have seen better performance when using mlx exclusively. Some interesting facts about the library I'll just throw in right here when you're working with NumPy. For example, if you have an array such as random ints and you maybe want to convert it to NumPy, it's very easy. You can just do numpy.array. So this is the only thing you need to do. However, if you're using a list, let's say like this, and you do something like, I'll just do a quick print statement. Oh, accidentally pressed shift. So it works. However, from what I know, this is slower than NumPy conversion, so you might want to play around with it. So be careful with list conversions, especially in your training loop. I'm glad you stuck through. I hope you learned something new, and I'll try to post a new video about more advanced topics in the next month. Subscribe, turn the noti bell if you want on, and I hope seeing you in a new video. Keep coding, keep grinding, and see ya.